Welcome to Lecture 28, where we will continue to talk about the design of sequential circuits. Now, you will recall that in Lecture 26, we were looking, or we had the goal of designing a sequential circuit that would output a 1 when the last two inputs, or you might say when the last input and the present input were the pair 0, 1, but would output a 0 at all other times. And we have considered the design of this circuit using both T flip-flops and D flip-flops. Well, today, in this lecture, we'll consider how we might go about designing this circuit using JK flip-flops. And we'll see some new wrinkles that will arise when we use the JK flip-flops rather than D or T flip-flops. So from the, let me just remind you of what we did from the description of the problem. In other words, that is that we want to detect the sequence 0, 1 and output a 1 in that case, but a 0 in all other cases. From that description, you will recall that we came up with a state graph. And then from the state graph, we came up with a state table. And then from the state table, we came up with a transition table. Once we had the transition table, our next goal was to find the excitation table. But of course, in order to get the excitation table, we needed to know what kind of flip-flops were being used. And as I mentioned already, we have considered previously the use of D and T flip-flops. So now we'll see how to get the excitation table when we're using JK flip-flops. Now keep in mind, we could use one kind of flip-flop for A and another kind of flip-flop for B. So far we haven't done that, and we won't in this case either. We'll assume that both A and B are the outputs of JK flip-flops. But just keep in mind that we could have perhaps say a T flip-flop for A and a JK flip-flop for B, or a JK for A and D for B. So a number of possibilities there. So, but again, in this case, we'll consider JK flip-flops for both. And so we'll say, what will the excitation table be? Remember, our ultimate goal is to find what the circuit will be, but the best way to find that out is to next consider the excitation table. So we ask, what will the excitation table be in this case? And again, this is going to be rather interesting. So let's see how it goes. We have present state, A and B, and then we want our excitations. So we'll have we'll say JA KA for x equals 0 and x equals 1, and JB KB for x equals 0 and x equals 1. Now, of course, JA and KA are the JK inputs to the JK flip-flop whose output is A, and JB and KB are the JK inputs for the flip-flop, the JK flip-flop whose output is B. And then we'll have the output Z for both x equals 0 and x equals 1. Now, I think it would be great if you already feel confident enough to fill in this table. And so I strongly encourage you to give that a shot. But if you don't feel quite up to it yet, then you can just stay tuned, and we'll go ahead and look into it right now. So let's see what happens. Now, remember that in order to do this, in order to fill in this table, we're going to need to continue to refer to this transition table that is immediately above it. And so let's just go one step at a time, and remember also that in these in these two columns here, the two numbers refer to the next value of A and the next value of B, A plus and B plus. Okay? So now that we're keeping that in mind, let's begin to fill in this excitation table. Okay, well, in the first case here, we have A is equal to 0, and the present value of A is equal to 0, and the next value of A is equal to 0. This is in the x equals 0 column. Again, present value of A is 0, next value of A is 0. Now, if A is the output of a JK flip-flop, how can that happen? How can we go from present state A to a present state of 0 to a next state of 0? Well, there's two ways that can happen. One way would be if we had 0, 0. Because remember, when a JK flip-flop has J and K both equal to 0, then the output will stay the same. And in this case, that is what's happening. A is initially 0, and then the next value of A is also 0, so it's staying the same. So 0, 0 is one possibility for JAKA. But that is not the only possibility. Another one is 0, 1. Because remember, when a JK flip-flop has J equals 0 and K equals 1, that says, regardless of what the present value is, make the next value of the output equal to 0. And since the next value of the output here is 0, that would also be sufficient. So if 0, 0 would work, and 0, 1 would also work, then we can summarize that very nicely by saying 0 and maybe D for don't care. Because whether really what we're saying is we don't care what KA is in this case. It could be either 0 or 1, and either one will work just fine. It will give us a next value of 0 up here. Now, this is the first time that we've seen don't care conditions appearing in any of these tables we're doing, so that may be a little surprising to you, but let's continue and do a couple more, and then I would very strongly encourage you to try to do, to turn off the video and try to do some yourself. So let's go to this next one. Here, A is equal to 0, present value of A is 0, and the next value of A is 1. So what values for JA and KA will make that happen? Well, one possibility would be 1, 0. Because for a JK flip-flop, when J is equal to 1 and K is equal to 0, that says regardless of whatever the present value of the output is, the next value of the output will be 1. And that is what we want. We want the next value of the output, A, to be 1. But 1, 0 is not the only possibility. Another possibility would be 1, 1. Why? Because when a JK flip-flop has J and K both equal to 1, that says toggle the output. And that's what's happening here, is that the output is originally 0, and it gets toggled to 1. So either 1 0 or 1 1 would suffice here in this case. And again, just as before, we can neatly summarize that by saying 1D. So I hope that you're already getting the hang of this and can fill in the rest of this column and this one and this one and this one. So I really do think it would be great for you to stop the video now, take a few minutes to try to fill in the rest of those, and then resume and see if you were correct. Okay, so let's go to the next one now. We go from present value is 1 to next value is 0. Okay, how will that happen? Well, one way that would happen would be if we had 0, 1, because whenever j is 0 and k is 1, that says the next value of the output will be 0 regardless of whatever the present value is. So that would be good. That would give us our 0 here. But another possibility would be 1, 1, because 1, 1 will make the output toggle, and that's what's happening here, is we're going from a value of 1 to a value of 0, so the output is toggling. So if either 0, 1 or 1, 1 is fine, then that means we could write this as D, 1. And now for the next one, we go from a present value of 1 to a next value of 1. And what will do that? Well, 1, 0 is one possibility, because if j is 1 and k is 0, then the next value of the output will be 1 regardless of whatever the present value is. So 1, 0 is one possibility. And another one is 0, 0, because if we had 0, 0, that says keep on with the same output, and that is in fact what we did in this case. So if 1, 0 or 0, 0, if either one of those will work, then that can be summarized as D, 0. So the rest of these I'll go ahead and fill in a little bit more quickly, because I think the explanation now is probably beginning to get a little redundant. So now we can, now if we want to fill in this column next, that means we need to look over here in this table up here. We need to look here at these numbers in the x equals 1 column, and we need to look at the first number in the pair in each case. Okay? Now you will rapidly notice that those numbers 0, 1, 0, 1 are exactly the same as we had over here, the first numbers in the pairs in this column, the x equals 0 column. So we're going to get exactly the same answers: 0, D, 1, D, D, 1, and D, 0. And so now we're ready to go to JB and KB. So we, for the x equals 0 column, we come back over to here, but now we're looking at B rather than at A. Okay, now one thing we can say right away is that we see that in this x equals 0 column, the next value of B is always 0. So that means, remember that for JK flip-flop, if J is 0 and K is 1, that means regardless of the present value of the output, the next value of the output will be 0. So therefore, 0, 1 is one possibility for J and K in each one of these cases. But it's not going to be the only possibility. So now we need to go back and look for the other possibilities. Okay? Now, in the first case, when B is, present value of B is 0, and next value of B is 0, another possibility for J and K that would make that happen is 0, 0. Because that says keep doing what you're doing. In the next case, we have 1 going to 0, and that could be the result of a 1, 1, because it's a toggle. Here, 0 goes to 0, and that could be 0, 0. And here, 1 goes to 0, and so that's 1, 1. And now if we look at each one of these cases, we come back up here, 0, 1, and 0, 0. That could be put as 0D. The next two, 0, 1 or 1, 1, could be summarized as D1. 0, 1 or 0, 0, 0D. And finally, 0, 1 or 1, 1 is D1. And now we're down to the last column here. And notice that in this column, this is the x equals 1 case, and we're looking for next value of b, which is always equal to 1. And so definitely one possibility for JB and KB would be 1, 0. Because 1, 0, if J is 1 and K is 0, the next value of the output will be 1 regardless of the present value of the output. So 1, 0 is definitely a case, but what are the other possibilities for J and K? Well, 0 going to 1 is a toggle, so we have 1, 1. 1 going to 1 is a case of staying the same, so that's 0, 0. 0 going to 1 is a toggle, so that's 1, 1. And 1 staying at 1 is 0, 0. And so now each one of these, of course, can be summarized more briefly. The two up here, 1, 0 and 1, 1 is 1D. 1, 0 and 0, 0 is D0. 1, 0 or 1, 1 is 1D. And 1, 0 or 0, 0 is D0. And of course, the output is just the same as before. So 0, 0, 0, 0, 1, 0, 1, 0. And that completes the excitation table when we have JK flip-flops for A and B rather than D or T flip-flops. So I hope that was clear to you. And now, just as we did before, we want to, the final step before we can go ahead and draw our our circuit, is to find out functional expressions for our excitations and our output in terms of the states and the input. So in other words, we want to find JA, KA, JB, KB, and Z, all 5 of those, as functions of X, A, and B. So let's get started with this. Well, first of all, we know, we've done this problem now a couple of times, and we know already that Z is equal to X, B prime. That doesn't depend on the kind of flip-flop that you're using. And so just as Z was equal to XB prime in the case of D flip-flops and T flip-flops, so it will continue to be equal to XB prime in this case of JK flip-flops. And that's easily verified by looking up here at the output Z, because you can see when X is equal to 0, the output is always 0, and that's consistent with this. And then when X is equal to 1, we have 1, 0, 1, 0. But if X were equal to 1 here, then Z is equal to B prime, which B prime would be 1, 0, 1, 0. So it's easy to see that this is the correct expression for the output z, once again, just as it was in the previous cases. So now we just have the four excitations, JA, KA, and JB, KB, that we need to find expressions for. So let's see how this will go. We'll start with JA. Now, remember that JA is the first number in each one of these pairs, and KA is the second number. Also remember that for x equals 0, we're going down this column. So the x equals 0 row of the Carnot map refers to the data here in this column. Okay, so JA will be 0 when A and B are both 0. So here we have A is 0, B is 0, so JA will be 0. When A is 0 and B is 1, it will be 1. When A is 1 and B is 0, it will be a don't care condition. And remember, for the don't care condition, we're looking for minimal sums now. So we'll put that as a squiggly 1. So that's, again, 1, 0. So we'll put one of our squiggly ones there. And when A and B are both 1, we have another don't care condition. So this is what we have for JA when x is equal to 0. And now when x is equal to 1, we come over here to this column. And when A is 0 and B is 0, we get 0. When A is 0 and B is 1, we get 1. When A is 1 and B is 0, we get don't care. And when A and B are both equal to 1, we get another don't care. So that's the Carnot map for JA. And now let's look at the Carnot map for JB. Excuse me, let's do KA. And I think that I'll save JB and KB for the test. Okay, if you are, well, I hope that you'll try to fill in this table yourself first. I hope you'll stop the video and try to fill in the Carnot map yourself, and then come back and see, check your work. Okay, so let's see how this goes. We're now looking for KA, which is the second number in each one of these pairs and each one of these pairs. First, we'll go for x equals 0, so that's the top row of the Carnot map. And when A is 0 and B is 0, KA is don't care, and the same when A is 0 and B is 1, it's a don't care. So we'll get a squiggly 1 here and a squiggly 1 there. Now when A is 1 and B is 0, we want KA to be 1. So we come over here, A is 1 and B is 0. That will give us this 1 here. And then finally, when A and B are both 1, we want Ka to be 0. And notice, by the way, I'm in the kernel map, I am filling in zeros now. But if you don't want to do that, you remember when we talked about using kernel maps before, we said that generally we would fill in either ones or zeros, but not both. Here I've been filling in both, so I'll continue to do that, but keep in mind that it's not necessary. Okay, so that's Ka for when x is equal to 0. And now we'll look in this column to find Ka when x is equal to 1. Well, again, the first two values will be don't care conditions, so we'll get squiggly 1s there and there. And then when A is 0 and B is 1, we get a 1. And when both A and B are 1, we get a 0. So those are the kernel maps for JA and KA. And now let's go ahead and find expressions for JA and KA. So we'll look first for JA, and we'll talk about the prime implicants here. And there are no rectangular groupings of 8 one-cells, but we do have some rectangular groupings of 4 one-cells. One is this. And that will simply be equal to B. Another one, another rectangular grouping of 4 one-cells is that. And I hope that you are convinced that the appropriate name for that is A. And that's all of the rectangular groupings of 4 one-cells. And when we look at rectangular groupings of 2 one-cells, there are no rectangular groupings of 2 one-cells that aren't completely contained within one of the prime implicants we've already identified, and likewise for rectangular groupings of 1 one-cell. So this is it. These 2 prime implicants are the only prime implicants we have in this case. Now let's look for essential prime implicants. Well, remember that in order to find essential prime implicants, the first step is to find essential one-cells, and this one-cell is essential, and this one-cell is essential. Clearly, these 2 one-cells are not essential. They couldn't possibly be because they are shared by 2 prime implicants. Now, these 2 one-cells, if these were ordinary ones, these would be essential because they are contained only within this prime implicant. However, remember, these are don't care conditions, and don't care conditions can never be essential. Therefore, the only essential one-cells are these 2, and both of those are in the same prime implicant, namely B. So B is the only essential prime implicant. And now when we look for minimal sums, we only have one minimal sum here, and that is JA is equal to B. How do we know that it's the only one? Well, if we shade in, we start out, remember, when we're coming up with minimal sums, we always start out with what's essential, so we must include B since it's essential. And then if we shade in B, okay, we'll shade this in like that, and now we ask ourselves, is there anything else that must be accounted for? And the answer is no, because these 2 are don't care conditions, so we don't have to account for those, and therefore we're done. So the minimal sum for JA is simply B. Now let's look for the minimal sums for KA. Okay, once again, there are no rectangular groupings of 8 one cells, so we look for rectangular groupings of 4 one cells, and one such grouping is here. And the name of that prime implicant, I hope you'll agree, is A prime. And there is another grouping of another rectangular grouping of 4 one cells, which is these two and these two. And the name of that will be B prime. And there are no more prime implicants. So now we look for essential prime implicants. And just, we can make this quick. We know that these are the only two essential one cells. So that means that B prime is the only essential prime implicant. And therefore, the minimal sums, there's only one, and it is Ka is equal to B prime. And if you decide to shade this in, you get that. And you don't need, that is sufficient. You don't need to account for these two terms because they're don't care conditions. Okay, so we now, of these quantities here in this excitation table, we have now solved for Z is equal to XB prime. We have found JA, it's equal to B, and we have found KA, it's equal to B prime. So now let's talk about our test. This will be 28.1. Find all minimal sums for JB. Actually, I guess I'll maybe list these vertically. So we'll have A, B, C, and D. And then 28.2, find all minimal sums for KB. And then 28.3 will be in class. And I'll break now for just a moment to fill in A, B, C, D for 28.1 and 28.2. We'll talk about those and then we'll be done. So now we're ready to finish our discussion of the test for lecture 28. So up here remember, we have found this excitation table, and we have found expressions for JA, KA, and Z as functions of X, A, and B. And now you're, and those were minimal sum expressions. And now you're supposed to find minimal sum expressions for JB and KB using this information up here. You're supposed to find minimal sum expressions for JB. I'll go ahead and spell it out. JB of X, A, and B. And here KB of X, A, and B. You're supposed to find minimal sums, find all minimal sums for both of those. And your choices here are JB is, it's still, the variables are X, A, and B on all of these. So if you want to, you could change this JB. Each one of these JBs here could be changed to JB of X, A, and B. And likewise here, all of the KBs here, you could change to KB of X, A, and B. I've just written it more concisely. So anyway, your choices are for 28.1, JB equals X prime and JB equals B prime. So you have two minimal sums, those two. In B, you also have two minimal sums, JB equals X and JB equals B. In C, you have only one minimal sum, JB equals X prime, and in D you have the single minimal sum JB equals X. And for 28.2, same kind of situation. In A, you have two minimal sums, KB equals X prime and KB equals B prime. In B, you have two minimal sums, KB equals X and KB equals B. In C, you have the single minimal sum, KB equals X prime, and in D, you have the single minimal sum, KB equals X. And then 28.3 will be given in class. So that completes our the test and all of our discussion for lecture 28. So good luck.